Okay, we finished the previous class in the middle of the discussion, right, of logistic regression. So let's go ahead and go back to the problem that we were addressing. So start jump, okay, and I believe we were looking at the universal bank file, right, the one that we actually used before when we discussed classification trees. Classification model. Okay, so this file contains data on 5,000 people, right? Customers of the bank, and the bottom line, the idea behind this data set is: will we be able to predict what type of customers will be willing to take a loan from the bank when we offer it to them, right? What are the important variables? And what are the important characteristics of people who can be targeted and likely accept the loan from the bank? So therefore, our target variable is this one right there, personal loan, right? And you can see that it's labeled as a categorical, 0 or 1. 1 for people who did get a loan, 0 for people who didn't, right? And everything else is our predictor. Now note that zip code we excluded, right, from consideration. Why? Do you think zip code is not a valid predictor? If I include can I include the zip code? I can, right? I can include anything, really, in my model. So could it be that in certain zip codes, my model will say that in certain zip codes, people are more likely to accept the loan than people in other zip codes? It's possible, right? But what can be the reason behind certain zip code, let's say, people really are willing to accept a loan? What could be possibly the reason?
Different income levels in different zip codes.
Income levels, right? Certain zip codes, exclusive neighborhood, right? Mostly, high-paying people live there. Like in Williamsburg, it would be what? What's the rich area in the Williamsburg? What's it called? Kings Mill. Ever heard about Kings Mill? It's basically a golf course, right, with houses built on the golf course. So that's pretty expensive neighborhood, and people with high incomes live there, right? So if we include zip code, it's possible that Kings Mill area will be showing up as big likelihood that people from the zip code will get a loan if offered. But again, just like Michael said, it's because of income, right? And we have income there already, right? Income right there. So therefore, zip code seems to be a redundant thing, okay? So here's what we did in the previous class, if you remember. We said probably, and that is just our guess, right? Income is the strongest predictor that will tell you whether or not a certain person is likely to accept a loan. So let's use for now very simple model, right? And let's go ahead and build the model. So what we did in the previous class, pretty much, right? Personal loan is my target, 0, 1, and my income is the predictor, so model effect, okay? Also, one thing that we discussed, I have to specify for jump which level I'm really targeting, right? So personal loan has two levels, 0 turned down the loan and 1 accepted the loan, right? So obviously as a bank I want to predict who will likely accept the loan. So naturally my target level is 1. So when I run this model, here is my output. And if you remember, we discussed that how the logistic regression really works is it's trying to predict based on the values of all of my independent variables. It's trying to predict the probability, right, of certain event happening. In this case, it's the probability that a customer, if I approach them from a bank, they will accept the loan. And the function that is used in logistic regression looks like that. Looks like kind of stylized, long, really long, and kind of flattened out letter S, sigmoid function, right? And that's what it is, essentially. So the output, excuse me, the main output from my model is right here, where it says intercept and income. Minus 6.127 is the intercept, and the slope for the income is 0.0371. So my model is just like that. So in order to predict the probability of getting a loan, probability of 1, all I have to do is compute this expression, 1 plus e to the power minus 6.127, if I remember correctly, plus 0.03, oh god, I need to go back. So 6.127, 0.0371. 0.0371, and I have to multiply it by the income level. Okay, so if I do these computations, then the model will basically tell me what's the probability. And after that, I need still to classify this observation. Right. So let's run a couple of examples. Now I want to point out that in my file, let's go back to jump file. No, that's not it. That's Excel. In my jump file, let me go back to the original one, right? If I look at the column income, it contains numbers. So what do you think this number 49 means? Income equal 49. 49 what? $1,000, right? So my income in the file is recorded in terms of thousands of dollars, right? Okay, cool. For example, let's say a person comes in with an income of $100,000, okay? What's the likelihood for them to get a loan from me? Well, easy, right? So probability, or remember we call it also propensity, right? Probability, another word for the same thing is propensity. What's the propensity of the customer with income $100,000 to get a loan from the bank, okay? So all I have to do is do the computations. 1 divided by 1 plus e exponent, right? Of plus 6.127 minus 0.0371, and because all incomes are in terms of thousands of bucks, if I multiply it by 100, it's the same thing as $100,000, right? Because the model was built on these numbers that are expressed in terms of thousands of dollars, okay? All right, well, let's go ahead and compute that. But even visually, if I use this nice curve, okay? So $100,000 is somewhere over here, agree? So visually speaking, do you think it's a high probability? According to my picture here? No. I actually expect the probability to be around probably 0.1 or something like that, okay? Even if I'm looking at this curve visually, right, kind of eyeballing what the probability is going to be. But let's go ahead and compute that. So I'm just showing you how this model is used when it's constructed, right? So probability, now let me make it bigger so that you can see better. Okay, probability of getting a loan equals to 1 divided by 1 plus EXP, right, of, well, let's kind of put the full expression, right, minus, and then I have the regression. My regression is what? Minus 6.1273, okay, plus my slope is 0.03712, and multiplied by 100,000, that means dollars, right? So I close the brackets for the regression, I close the brackets for the exponent, and the last one is like that. Okay, so when I hit enter, there it is, okay? The propensity of such customer with income of $100,000 to get a loan from my bank is 8%. Now I need to say, is it a 0 or is it a 1? And we discussed that in previous class, right? What cutoff point do I use as a judgment point? Same, good old body standard, 0.5, right? If it's below 0.5, then I'm classifying it as a 0, no? So this one, 0.08 closer to 0, so therefore it's a 0, right? Okay, so this customer likely will not get a loan from us, right? Even if we offer it to him or her, right? So therefore, there is no point even trying, so to speak. Well, I could do the same exact thing using the built-in tool, right? So let's go to the red triangle menu, and remember how it's called? Profiler, right? It's called Profiler. So if I call the Profiler, there it is. So here All I have to do is really replace my number with the income, 100,000, and there it is, okay? It says the likelihood of 0 is of 1 is 0.028, pretty much exactly what I computed, isn't it? Yeah, 0.028, okay? So it's more likely, oopsie, I'm back, right? 100,000. It's more likely that this type of customer will not get a loan from us, okay? All right, now, what can we see about the kind of direction of this model? Where does the model go? As the income becomes higher and higher and higher, what happens with the probability of getting a loan from the bank? It is going better, right? So, therefore, well, actually, let's play around, right? Let's kind of guesstimate what would be the threshold, critical value, right? Above certain threshold, the likelihood will switch to higher than 0.5, and we'll classify such customer as a 1, right? So how about 130,000 bucks? Kaboom. Probability of yes is 0.21. Still no, right? How about 150? 150 is 0.36. Likelihood of getting a loan. Still no, right? How about 160? For 160, 0.45 likelihood of no, of yes, versus 0.54 likelihood of no, right? Still, we're classifying that as a 0, okay? How about 170? Let's take a look. 170. Yeah, 170 things switch, right? So now the likelihood that this type of customer will get a loan from us is actually more than 0.5. Therefore, we're classifying that specific customer as a 1, and therefore it makes sense to contact him, right? So somewhere between 160 and 170 was our value, right? Let's try 165. Let's see if we can get it. All right. So if it's 165,000 bucks, we're right on the money, right? So apparently, according to this model, right, anybody with an income of 165 and below is a no-go, pretty much, right? They will not agree to taking a loan from the bank. If the income is above 165, that's when we're getting a yes from the customer, right? Okay, now that actually brings an interesting point of discussion. Let me kind of bring it up. True or false, ladies and gentlemen? These were my original, from my jump output, this was my intercept, and that was my slope, right? Okay, so what can we see? Well, here, it's the same expression, right? So instead of 100,000, I'm going to say times income, whatever the level of income is, okay? So my slope from the model that I obtained by using jump, okay, slope is positive. And what we discovered just now, as the income gets higher and higher and higher, the probability, the likelihood of a person taking a loan out of the bank is getting bigger and bigger and bigger and bigger. Which makes sense, right, on the intuitive level. Yeah, if I'm making a lot of money, do I mind taking out a loan? No, probably, right? If they tell me, hey, do you want to build another, room, right, to your home, or do you want to buy Tesla Model S, 75,000 bucks car? I'm like, yeah, I'm making 300 grand a year. Why not, right? Let me take a loan out. I'll buy this car, right? But what if I'm making $40,000 a year? Can I afford Tesla? No, I cannot, right? So therefore, it only makes sense that people with higher incomes, they are more likely to agree to the loan when offered. That only makes sense, right? And we got a confirmation, okay? So here is my my model right there, okay? So what it says basically is as income is getting higher, right? As income is getting higher, the probability is getting larger. Well, let's see if it makes sense, okay? What happens if income, let me rewrite this expression a little bit, okay? Equals to 1 divided by 1 plus exponent of, what's this? This one is e to the power plus 6.127. That's it, right? Times e to the power minus, so I'm going to write it as exponent of minus 0.0371 times income, okay? So what happens if my income goes up, okay? certain level of income, I go income plus 1. In other words, I started to get an extra $1,000 per year, right? My income went up. Okay, so that means that this expression under the exponent is getting larger, right? Income gets larger, so this expression gets higher, but it's minus sign, right? So therefore, e to the power minus a larger number gives me what? A smaller number, right? Remember how exponent looks? This is how the exponent looks, okay? So if I'm getting into the negative area, right here, which I am, right? I'm getting higher and higher and higher negative number. And if I'm raising e to the negative power, it's getting smaller and smaller and smaller, okay? So this whole thing, because that is the part of the expression, I'm multiplying by a smaller and smaller and smaller number, right? Income goes up, that number goes down. So therefore 1 plus this number goes down as well, right? So therefore I'm dividing by a lower number as income increases. And if I'm dividing by a lower number, I'm getting a higher number, right? That basically explains in a messy way why income increase results in the probability increase. And that's exactly what we saw, right, on the output. This one right there. It says income goes up, your probability of getting a loan, agreeing to the loan, it also goes up, okay? So therefore, simple rule of thumb, ladies and gentlemen. If I have this type of output from my jump analysis for logistic regression, by just looking at my slope, not even a number, but the slope itself, the sign of the slope, is it a plus or is it a minus? If the slope is positive, how does that impact the probability? The increase in the predictor variable results in higher probability or lower probability? If the slope is positive. Higher, right? We just discussed it, right? So positive slope results in a higher probability, as you can see, right? Income goes up, probability goes up, okay? And the slope is positive, right? Negative slope, other way around, okay? All right, now let's discuss one more thing. Now, that's going to be brutal, I promise you, based on my experience from previous semester, okay? All right. I'm kind of regrouping myself, right, to get into this murky waters. All right, if you remember from yesterday, not from yesterday, from the previous class, right, we said that what we're calculating with logistic regression is probability, or what's another word for probability? Propensity, right? Propensity, right? And that is exponent of minus beta 0 minus beta, let's do it like that, plus beta 1 x1 plus etc. plus beta k xk. And you understand, I hope, that how many variables can I add to my model? As many as I want to, right? The more the merrier, or you would think so, right? It's going to make things better because I can predict better, can follow my data closer and closer and closer, okay? And then we did some manipulation, if you remember, in the previous class with the expression. And this is what we ended up with. We said that this is the same thing as to say natural log of p divided by 1 minus p is equal to beta 0 plus beta 1 x1 plus beta k xk, right? We said that these two expressions essentially is the same thing. One means another, and vice versa, okay? Remember how we call this awkward ratio p divided by 1 minus p? How did we call that? Odds, right? We call this odds. And we said that odds and probability are interchangeable, right? I can say likelihood of certain event is 30%. That translates into the odds of 1 out of 2. Okay? If probability is 50%, that translates into the odds 1 out of 1. If the probability is 80%, that translates to the odds of 4 versus 1. Okay? So there is a 1-to-1 correspondence. Odds and probabilities are just different language to describe the same phenomenon, right? And we said that probabilities and odds move in the same direction, right? If the probability is getting higher, the odds are getting higher. If the probability is getting lower, the odds are getting lower, okay? So these are just two different ways, different languages to express the same idea. Okay? Cool. So now let's do this. I'm going to erase that. And after that, let's raise e to the power of left-hand side and also to the power right-hand side. Because my right-hand side and left-hand side are the same, I'm going to get the same thing, right? So therefore, on the left, I'm going to have p versus 1 or minus p, or, just as Michael pointed out, odds of certain event, right? And on the right, I'm going to have e to the power beta 0 plus beta 1 x1 plus beta k xk. Okay. Now, let's use, you remember how we interpreted the slopes of regression when we discussed linear regression? Like, say, for example, we predicted the price of the car versus mileage, right? And the slope was like 0.06, blah, 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 right? What did we say? If mileage goes up by 1, that's the impact on the price of the vehicle, right? Price is decreased by the amount of slope. Minus 0.06 means every mile reduces the value of your car by 6 cents. That was a straightforward interpretation, okay? Wouldn't it be lovely if we had this straightforward interpretation here as well? Unfortunately, it's not as clean. But still, it can be interpreted. So let's get with this, okay? So here's what I'm going to take. I'm going to take this expression and kind of, you know what, I'm going to erase all that. Give me a sec. Okay, good. So suppose that I'm sitting, and let me get back to my good old model, right? So e to the power minus 6.127 plus 0.03, oh gosh, what was that? 0371. Okay, 0371 times income. So this is the model that I have right now, right? Predicting the odds of getting a loan out of the bank if I know the income and nothing else. Okay, good. Suppose, let me get to the same practice, just like what I did before for the linear regression. What happens if the income is increased by 1, right? I'm trying to get interpretation out of this thing, okay? So, therefore, whatever my income was, okay, I'm going to call it old income or whatever, right? I'm getting 1,000 extra bucks from my employer. Isn't that nice? Yeah, so income goes to income plus 1, right? What happens with odds of getting a loan? Let's discuss that, okay? According to this expression, okay, I can compute my new odds, right? So this, let me call that old odds, right? This is my old odds. ODDS, right? With my income as it was before the raise, okay? Now I got a raise. So income I have to replace by income plus 1, agree? So therefore, let me compute new odds. New odds are equal to, all I have to do is replace inc with inc plus 1, right? And that's it. So e to the power minus 6.127 plus 0.0371 times, and here is this creative part. Income becomes income plus 1, right? Okay? Now let's unwind this expression. So, if you ever took, it's not even calculus, it's more like algebra, right? Or is it calculus? Is it in the calculus domain, dealing with exponents and logarithms and functions? Now let's call it calculus. So, here, right, e to the power minus 6.127 plus, I'm going to open up this expression, 0.0371 times my old level of income, before the raise, right, whatever it was, plus, I get an extra 0.0371 because of this 1 right here, agree? Okay. So therefore, really, here's what happens. I can rewrite this expression like that. E to the power minus 6.127 plus 0.0371 times the level of income, which was old, times e to the power plus this one right here, 0.0371. Okay? I'm just doing mathematical juggling. That's it. Nothing more than that. Okay? Now, ladies and gentlemen, tell me, what is this expression right here? I'm going to highlight it red to emphasize its importance. Okay? So this part, what is that? That's my old odds, right? This is the same as right here. So therefore, this is nothing, none other than old. Let me write it out. Old odds. Okay. All right. So therefore, ladies and gentlemen, here is the bottom line of it. Okay. It looks like my new odds of getting a loan after I got a raise by $1,000 from my employer, right, are equal to the old odds, double D, right, old odds, multiplied by this, whatever it is, numerical, right, e to the power plus 0.0371. Or alternatively, I can rewrite it like this, okay, new odds divided by old odds, so I divide everything by old odds, right, this cancels out from here, are equal to e to the power plus 0.0371. Okay? So all of that is just a bunch of mathematical juggling, right, to get to this expression. So after I had an increase in salary, well, we just discussed, higher income means higher propensity to get a loan, right? I have more income, therefore my odds or probability to get a loan from the bank should go up, right? By how much? That's the answer for you, okay? The ratio of odds is equal to e to the power of, and what is this, by the way? Can you remind me? This is my slope, right? It was the slope of the original regression equation, right? That came out of my model, right? So you see how slope in the case of logistic regression does not have a clean interpretation, right? I have to take the slope and raise the e to that power, okay? And then it can be interpreted, okay? So it's more complicated. The interpretation is more complicated than it is for the linear regression, but we still can interpret it. Well, now let's calculate this e to the power blah blah blah, whatever the number is, right? So I'm going to get back to my Excel. I'm going to say, well, according to my interpretation, which I just created, new odds divided by old odds, okay, that is equal to exponent of what number? Of that number right here. Slope for my income, beta 1, right? And that would be 0.3712. 0.3712, okay? Kaboom. And it says 1.0378. Okay? 1.0378. Any questions about what we just did? Are you bored out of your mind? Yeah? Bad news, guys. This is how the new world looks like. So if you want to be rich and prosperous and successful, you better get used to it. Okay? There is a new sheriff in town. It's called data analytics. Okay? So, ladies and gents, it basically says, what does this say, by the way? That my new odds are higher or lower? This expression right here. Somebody say it. Somebody say meow. Yeah, meow. So this rate, if new odds divided by all odds are equal to 1.03, are the new odds higher or lower? Higher, right? The ratio is greater than 1, so therefore new odds are higher. And that actually is in line with our probability. We said income goes up, probability goes up, therefore odds go up, right? So it says basically, and this is, by the way, universal ratio, right? Does it say anywhere what my base income should be? No, it doesn't, right? It says that whatever was my old income, if I'm getting raised by $1,000, that is the universal number, right? The odds ratio will go up by 1.0378, right? Now, ladies and gentlemen, I showed you actually a hard way to get this number. Do you want to see an easy way? Now let's do the easy way. I go back to my analysis, okay? And can you guess where I'm looking? In what place? No, red triangle, right? Red triangle. That was, yeah. Everything that you may want to get in addition to the, the standard reporting is in red triangle. You see the item that says odds ratio. Let's call it up. Odds ratio. Do you realize that what we just computed is odds ratio? New odds divided by old odds, right? That's odds ratio, okay? So therefore, if I call it up, look at that. It says unit odds ratio. Can you guess why it's called unit odds ratio? Because it corresponds to the increase of income by 1, right? So your independent variable goes up, odds go up. So it computes essentially the ratio for you of new odds versus old odds if your independent variable is raised by 1, by a unit. That's why it's called unit odds ratio. And because we have only one independent variable, which is income, right? That's the only thing that I used in this model. There is only one ratio. Is it the same thing as we computed or not? It is, right? It is. So I computed 1.03782, and what I have here is 1.03782. Well, 3, another decimal, right? So that's the mystery behind that number, okay? I wanted us to kind of suffer through it a little bit, but make a connection. So the connection really is this number, 1.03782, is nothing more and nothing less than e to the power of the slope of your regression, not linear, logistic regression, right? That's it, okay? Okay, any questions? Anything unclear, hazy, shady, weird? Let me show you one more thing, which seems a straightforward thing to me, but it creates a lot of confusion on the quiz and on the exam. And we're kind of due for exam soon. Wouldn't you agree? No? Baby doesn't like. Okay, well, we're going to have an exam, I'm guessing, next week? Or maybe in 10 days, or something like that. Yeah, that's what I mean, next week, right? Next Friday. Or the Friday after that. Okay, so let me show you an elementary thing which seems to put a lot of students in the state of physiological mental stupor for some reason that is unknown to me. Okay, so here. Let's go back to this expression right here. So, remind me one more time, this thing right there, how much was it? We just computed it. It's 1 point something something. 1.037 blah blah blah. It's an odds ratio, right? 0.03782. Okay, 782. Okay. All right. Here's what I'm going to do to make it kind of simple, right? And you will see why I'm doing this. I'm going to subtract from both parts, right side and left side, my old odds. Okay, so minus 1 times old odds from the right side, left side, and minus 1 times old odds from the right side. So what I'm going to get, let me erase all that. Oh, geez, it's going to be quite a challenge. Okay. So what I'm going to get on the left side is new minus old, right? Or in other words, increase, right? By how much my odds increased, okay? So odds increase. Going from my income to income plus 1, right? By getting extra $1,000 from my employer, okay? And at the same time, it's equal to 1.03782 times old minus 1 times old, which gives me 0.03782 times old odds, right? Agree? Yes, 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 agree, agree, agree. Did I tell you the story about yes, 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 agree, agree, agree? Yeah, I did. Okay, good. So this is what I'm getting, right? by how much my odds changed, right? I shouldn't say increase, I should say odds change, right? Well, it's technically increase, but odds change. Okay? Represents 0.03782 of my old odds. Okay? In terms of the percentage, this is the proportion, right? This is proportion. What percentage does that correspond to? 0.03782 corresponds to what? 3.782%, right? 3.782%. Agree? If 0 is 0% and 1 is 100%, then 0.03782 is 3.72%, okay? So therefore, what does this expression say? My odds, when I went from my base salary, whatever it was, to my base salary plus 1,000, my odds of getting a loan, accepting a loan out of the bank, increased by 3.782% of my old odds, right? Do you agree? Michael? Yeah? Amanda? Yeah? Okay. William? Yeah? So that's just basically clean interpretation, okay? I'm looking at this number, I could tell it right off the bat, but you never seen it before, so I had to go the long route, right? I look at this number and what do I see? Odds ratio is more than 1. That means that if the income goes up by $1,000, the odds increase. By how much? Well, 1 is my base, 100%, right? But now I'm getting 1.03782. So therefore, what's the difference? The difference is by what percentage my odds went up, right? So the difference between that number and 1 tells you what is the percent increase in the odds, okay? And that's nice, clean, fruitful interpretation, okay? How do you like them apples? Any questions? You're awfully quiet. Any questions? Is it getting too difficult or too confusing? Too much numbers floating around? All right. Okay. Well, what I wanted to point out is, in the time remaining, we have about, 6 minutes remaining. Remember what we did with our model when we studied linear regression. We evaluated every single variable based on its significance, right? Remember what we did? We did hypothesis testing, agree? Reminder, okay? Reminder of the hypothesis testing. Here's what we tested. We said for each variable we're going to test the following hypothesis. That this specific slope is what? Equal to 0. Which means that the variable I is significant? Insignificant, yeah. Variable number I is not significant, right? If I can replace slope with 0, effectively I'm taking it out of the equation, right? Variable is not significant. Okay, and alternative was that the slope cannot be set to 0, slope for this variable I, and therefore variable is significant. And how did we test hypothesis? We got the p-value, right? That's how we do it. You got the p-value, and then you compare the p-value against alpha. Is it less than alpha? Is it greater than alpha? If it is less than alpha, then you reject null, right? If it's greater than alpha, then you fail to reject null, right? Fail to reject null. So that's basically the idea behind it, okay? Same exact thing happens here, okay? Because essentially, in a nutshell, we have regression, only we don't use it as regression, we raise it e to the power of minus regression, we add 1, divide 1 by the whole thing, right? And you get probability out of that. But in the core of this model is still the linear regression, right? Yeah. So therefore, I can test the same darn hypothesis, right? Where do I see the p-value? I see the p-value in exactly the same place where I'm looking for the p-value dealing with linear regression. So here's my income slope, right? And at the end of the line where it says probability greater than chi squared, that's my p-value right there, okay? For this hypothesis. So I have only one to test because it's only one variable, right? Income. So in other words, here I'm going to ask myself, is income a significant, statistically significant variable in predicting the likelihood of a customer getting a loan out of the bank? Well, here's your p-value. P-value is small. What do? We reject the null, right? We reject the null in favor of alternative, and it says, yep, income is a significant predictor. Based on income, you can say something about how likely that customer is to take a loan out of the bank or not to take the loan out of the bank. Okay? So that's kind of regression diagnostics, right? In the next class on Friday, what we're going to do is we're going to go back to our big fat file in JUMP, and we're going to say, well, income is awesome, right? It's great. We just figured out it's significant. But how about the rest of them, right? Is age important? Is experience important? Family size, average credit card balance, education level. And by the way, we don't know yet how to deal with education level, right? Because what's different about education and the rest of the predictors? What's different about education and the rest of my predictors? It's categorical, right? What we were dealing with so far was purely continuous variable, right? Income, okay? And all of them except for education is actually continuous variable, right? But education is categorical. How does that change things, okay? So all of that we're going to discuss in the next class. So we're going to expand the model to include all these predictors, okay? And also we didn't discuss one important thing about the model. I got the model, but is it a good model or is it a bad model? How do I tell? Can you guess what we're going to use in order to assess the accuracy or goodness of fit? R squared is one way to go, and what's another one? Matt was in my office hours today together with Brandon, right? And we discussed just this thing, right? This is a classification model, agree? How do we judge the performance of classification models? By things that it does wrong, right? And things that it does wrong is called misclassification rate. That's exactly right, okay? Now, we have 2 minutes, okay? What I wanted to do is do this. Go ahead and get out of your folders that thing. It's the matrix of our tool set, right? So far we discussed 3 tools. Classification tree, regression tree, and multiple linear regression. This model that we just built in today's class and in the previous class is about classification, agree? It predicts the categorical variable for me, okay? Specifically, yes or no, will they get a loan or will they not get a loan? That's a categorical response. Based on what type of predictor? Which predictor did I use? Income, right? And income was categorical or continuous? Continuous, right? So therefore, predictor is continuous, target is categorical. We learned one tool, classification tree, we started with that. Turns out that logistic regression is another model which you can use, right, to predict the same thing. So we're kind of slowly but surely building our tool set, right? So these are competing models, right? Essentially, if I'm a data analyst working for a company and boss comes to me, I'm working for the bank, right? They say, hey, Dmitry, we would like to build a model to predict who will get a loan, who will not get a loan. Can you do something for us? Well, now I have a choice, right? I can run the regression, logistic regression, or I can run the classification tree and then compare them against each other, right? Which one does a better performance, shows me better results? I'm going to show it to my boss and say, hey, I ran multiple things. That's the one, okay, whatever it is. It can be regression, logistic, or it can be tree. Or later in the semester, we're going to learn another one, which is a killer tool. People know that under the name artificial intelligence. You probably hear this word a lot, right? Artificial intelligence is going to change our life. What is artificial intelligence? Well, in the world of data analytics, is a certain model that's called neural network. And we're going to study neural network in about, I'd say, a month or so. Okay? So you will actually see what does that mean, artificial intelligence, okay, at the end of this class. What's this magical, mysterious artificial intelligence model? And that can be used as well, okay, to predict your classification, 0 or 1. Okay? All right, that's it for today. We're right on time, like Hogwarts Express. So I'll see you Friday.